Okay. Good evening, everyone. So, welcome to the next lecture. So, I'm indexing by 0, so it's lecture 3. So, quick announcements. Again, as I said, use the discussion board for questions, especially now that you're 2 weeks away from submitting your assignment. You really need to, if you have any doubts, you really need to clear them up. And also, there's a feedback link on every lecture. So, for example, for today's lecture, you can give feedback after the lecture. The exam date is still March 29 because some students actually did not want to change the date. So that's that. The project first report is due in a month, right? And then assignment 1 is due in 15 days or 2 weeks. And the course website will be down for a few hours. I think from tomorrow night onwards. So today, this is a tentative list of topics that we're going to cover. Of course, some of the topics are not even described what they are yet. But today we're going to look at finish up some work that we started last lecture. Basically, finish up CNNs and some other details about neural networks. Okay. And towards the last part, we'll cover something called reinforcement learning. So before I jump into today's outline, one of the students asked me to quickly go through the assignment document. So let me quickly run over it. Okay, anyway. I don't know, can you guys see? Okay, so the assignment has, I guess, how many questions? 7 questions. So some questions require a little bit of hand-based answers, so you may want to type it up or write it in paper. So the first question is about backpropagation. Here you need to do the exercise that we did for an example function in one of the lectures, in the first and the second lecture actually. The second question is all about trying to understand gradient descent. So we kind of introduced one optimization technique in this class, and that's what we're going to run with pretty much throughout the class. And it's a algorithm called stochastic gradient descent, or the batched stochastic gradient descent. So it's just a variant of what is called gradient descent. So why does gradient descent or gradient ascent work for optimizing any continuous function? Through this question, you'll try to understand that basically. So in this question, as you see, we are just trying to fit the parameters of a linear model. So you are choosing M and C, and then you're trying to figure out from data what the M and C returned are if you do gradient descent to figure out M and C. Okay, so that's what this question is trying to address. So for the first and the second question, are there any questions about how to answer in terms of writing or plotting? Have you seen, have any of you gone through the assignment document yet? Yeah.
So, do you assume that 6 and 7 that it's a linear model?
No, I mean 6 and 7 you need to understand what a linear model is. So just see whether these are linear models or not. There are two different models, right? Here, there's a model here in question 2. I mean bullet point 2, and you kind of repeat it for a couple of other models, which are listed right here.
But should we use a linear model?
No, the model is given. The functional form of the model is given. It may be linear, may not be linear. You've been given the functional form of the model. As in f theta is given. You just need to fit the theta parameter, right? Loss is given. I think it's mean square error. Remember, in the first lecture, we were talking about data models, loss function, and optimization. So optimization technique is gradient descent. Loss function is root mean square or mean square error, and data is going to be your just samples, right? And the models are going to be the 3 models here. Any other question? Okay. So the third question is just trying to kind of make you write some Python function. So you need to understand Python function, how they're defined. So this just asking you to write the loss functions, right? Which is something we covered in the class. Yeah.
Can we have the test data or something to check if the function is working correctly?
You can plot the function for example 2-dimensional data set that we kind of looked at in lecture 1, right? We looked at 2D plots. So you kind of use roughly similar functions. So it's just that it's not explicitly written as a function in that example code. Here I'm just asking for an explicit function. You can illustrate how these functions look like if you want. So question 4 is the classification pipeline. Again, it's the same. It's very similar to question 2, but it's looking at a machine learning task, right? I think it's self-explanatory. Most of the answers will be based on your outputs of your code, right? You may want to write textual descriptions of what inside or try to address some of the what questions here, like 5, 6, 7 are asking some specific questions, right? So this is a regular classification pipeline. So if you find any difficulty here, you look at the examples that were associated with lecture 1, right? Lecture 01 on the course website, and then see what additional things they're asking you to do. Basically, the addition is going to be a cross-validation thing, and I think performance as a function of some other parameters, tweakable parameters. Yeah.
So we can use the internal gradient descent function, right? For this, or should we write out?
Where is the internal gradient descent function?
So the gradient descent iteration, right? So we have some functions in scikit-learn which you could directly use.
You can do whatever you want to answer this question. Yeah. But the thing is, the example scripts that we gave in lecture 1, they already have these updates. So if you want a black box and you don't know what's in the black box and you want to tweak it, that's fine. Unless you go through the scikit-learn's code, but otherwise you can reuse what's given. Number 5 is again is also based on one of the scripts given in lecture 1, right? So here we are changing few other parameters like relu, and like the nonlinearity is being changed here, and the hidden units are being changed. That's it, right? A couple of other parameters that come with this model: the number of hidden units and the nonlinearities used. Right. Number 6 is kind of important question where you use some small scale data sets. MNIST and CIFAR10 are some well-known data sets in the domain of vision. So we'll look at try to repeat questions 4 and 5 with these 2 data sets, right? And the third part is actually asking, instead of using the scripts provided in lecture 1, why don't you use Keras or TensorFlow to do the same thing? It's, at least in TensorFlow it's quite easy. In Keras it's quite easy to make a simple linear model or this feed-forward neural network. So try to do that in Keras. Okay. And number 7 is asking you to use a pre-trained convolutional neural network called the VGG model. Okay, we're going to touch upon this model today. it's asking you to post-process the VGG trained model. So we are going to look at, that's the context of this lecture. So you'll understand number 7 after this lecture. And the related data sets are given here. So use that. Any questions about what to answer, what not to answer? Okay, so let's get back on track. So today we're going to again quickly review CNNs and visualizing CNNs that we covered last time, and then we're going to make a transition into further trying to visualize what CNNs are doing, because it's not exactly clear how they're able to achieve human level accuracy in image classification, right? And then we're going to try to understand this topic of jumpstarting CNN. So if you remember the classification challenge, the ImageNet large-scale classification challenge, it had 1.5 million images and 1,000 categories, and the most recent winners were all big companies, right? One was Microsoft, one was Google, and so on. So what does a non-Google or a non-Microsoft deep learning team do? So we're gonna kind of focus on that today. So that's the jump-starting CNNs, and the idea is basically try to reuse what they have already done if they have provided something. Right? They've basically given us the weights of the neural network model. So how do you bootstrap on top of it? And then we're gonna kind of revisit a couple of topics. Basically, in practice, neural networks. So in the assignment, you're gonna be looking at cross-validation and a few other things. But there are some additional topics that kind of improve or have become common practice in modern neural networks. So we're gonna look at them. I've just categorized them into data-related enhancements and model-related enhancements, and then we're gonna try to just tie back to what these state-of-the-art neural networks do. So the CNN that we studied last lecture is a stylized is just a stylized, or I would say a version of a convolutional neural network. It's a convolutional neural network because it has convolutional layers, but you could always rearrange these layers in arbitrary fashion and create your own network, right? You could still call it a CNN, right? So we'll try to touch upon what these state-of-the-art CNNs look like, right? Okay, so quick review. So from last lecture, we kind of try to exploit the specific properties of images, like there's going to be hierarchical structure. For example, if you're trying to identify a car, there's going to be tires, there's going to be windows, there's going to be headlights, and so on. There's locality aspect in images. For example, there are going to be edges all over the place in an image. For example, in the image of a car, so there could be an edge detector which can kind of locally find out the edge, and then sorry, I'm talking about spatial invariance. Okay. So locality is all about finding edges, finding components first, and then trying to get the broader pattern. So there is local structure in the images. For example, the tire is not related to the windshield or the window. So first you kind of identify the local components and get to the overall picture. And spatial invariance is all about whether the car is in the top left or the top right or some other place in the image. You still need to identify it. So you may want some structure in your network which kind of is invariant to locations. So an edge detector is invariant to location, whether the edge is on the left side of the image or the right side of the image. The edge detector, or a neuron which can fire because of an edge, will fire irrespective of where the edge is, right? And that was the notion of filters. So we looked at 3 types of layers: convolution layer, pooling layer, and a fully connected layer. Fully connected layer is what we studied 2 lectures ago. It's the regular feed-forward neural networks hidden layer. Okay, and the key deviation from a feed-forward neural network was this notion of depth. So you can think of the input outputs or just the outputs of every layer to be a 3-dimensional array or a tensor. Okay, and each layer is just transforms an input tensor to an output tensor. So here I've just randomly stacked a few tensors, but there is this notion of depth which is important. And the convolution layer kind of capitalizes on something called parameter sharing. So the layer's parameters correspond to a set of filters. So a convolution layer, if you remember from last class, is basically composed of a filter, a set of filters actually. Let's say you arbitrarily choose the number of filters. For example, and the filter is specified by parameters such as filter width, filter height, and filter depth. Filter depth is going to be the same as the input tensor depth. And you choose a bunch of filters, let's say 10. Then there will be 10 such matrices which are called filters, and you use those 10 such tensors which are called filters, and you use those filters to glide over the spatial aspect of your input tensor and compute a single 2D activation map. So for each filter there will be an output activation map, which will be a 2D activation map, which will be a matrix, right? So that's kind of clear here. The filter depth is 1, let's say. So 3 cross 3 cross 1. It's gliding over an input tensor which is also of depth 1, and it's outputting a 2D activation map which is matrix. If there was depth here, the depth there will be multiple intermediate activation maps which should be just added coordinate wise or index wise, right? Okay. And the parameter sharing aspect was that all neurons in each depth slice, use the same weight and bias parameters. So a filter corresponds to the parameters of a neuron. So think of all neurons having the same parameters. That means they are all associated with the same filter. So that's the second point of view for the same entity, which is the filter, right? Okay. And the second layer that we looked at was the pool layer, which is quite straightforward. So if you have an input tensor, you work on depth slice by depth slice. On each slice, you kind of downsample the number of entries in that slice. A slice is just a matrix. So think of it, if the matrix looks like this, let's say I do something called max pooling, then with some parameters, let's say I'm looking at 2 cross 2 subregion, then I'm going to take the max of these 4 numbers, output it. So basically the output matrix is going to be half the size of the input matrix on each of the spatial dimensions. Okay. So if you so this is a stylized example where I'm just stacking a bunch of these con1 pool layers. So a con layer is has multiple filters, right? So let's say we have here 10 filters. So 1, 2, 3, 4, 5, 10 filters. Okay. So this is the filter operation. The filter outputting a single number. So that's the 2D activation map. And let's say I pass it through the non-linearity, because right after I get the activation map, I pass it through a non-linearity, right? Like ReLU. So that's the output of the activation map. So we are just looking at what are the outputs of the 10 filters, which is a set of 10 filters. What are the outputs after the con layer? So this is how the outputs would look like, let's say, for this image. Okay, and then these outputs. So this is again, I'm not representing the dimension. So again, this tensor has a depth of 10, right? This is again passed through another convolution layer, and that layer also happens to have number of filters as 10. And then I'm doing a pooling operation, and then again con pool, and so on. Okay. Only the last layer is a fully connected layer, which is passing through, which is connected directly to the loss function through your scores, right? So fully connected layer, the final W matrix is related to your score computation. So whatever the outputs here, whatever they are the outputs, so that times W plus a bias would be the score value. And let's say there are, I guess here there are, let's say 5 categories, then you have the W to be a dimension which has the number of rows to be 5, right? Okay. So let's actually look at one of the demos now from. So this is the same data set. so this is a in-browser convolutional neural network. Okay, and one of the dataset being worked on is the CIFAR-10 dataset that you'll also be looking at in your assignment. So okay. So here actually they are trying to define their CNN. So you can see the parameters that we discussed in the last lecture, like the number of filters, sprites, zero padding, what is the activation at the output of the conv layer, and so on, and pooling layer size and the stride, and so on. Okay, so what is this? Okay, so there is actually a way to preload. Okay, so this is an interesting demo where they're actually showing the input image and the activations that you see at each layer. So, for example, let's focus on the first layer. Then the input, then the layers dimension is 32 cross 32 cross 16, which means there are 16 filters. Okay, and these are the activations of the filters. Let's ignore the gradients because those are that you get when you do a backward pass. Okay, and weights are represented in this very small blobs here because the filters are of size 5 cross 5 cross 3. So does everybody understand how this, at least does everybody understand these two sentences there? Okay, so I think in this demo they're plotting the filters. So there are 16 filters here which are in the bottom part here, and which are of dimension 5 cross 5 cross 3, and the input is 32 cross 32 cross 3. Okay, and there are 16 such filters. So similarly you can see what happens. The ReLU is quite straightforward. It just thresholds these inputs so that high values remain bright and other regions become 0. So similarly you can look at what's the situation in the higher layers. Okay, it's not very informative. So here accuracy is quite bad. I don't know. Oh, I paused it. Sorry. So if I do a resume. So here you're actually able to see I guess the 3 predictions that it's making for each image, the number of times it's being wrong, right, and so on. Okay, so please go through this demo to get a better idea about the CNN. Okay. Okay. Now let's. So that demo I kind of interjected in between because. So what was the point of looking at those activations, right? I mean, it was not clear what the CNN was exactly doing. Yeah, it has a really good test accuracy or validation accuracy or training fit and so on. So last time we were trying to make an attempt to try to understand what's happening in the layers of the CNN. So we try to look at activations and weights, and this is what in the demo also they kind of plot. We also try to look at images in an embedded space. So if you remember, we were taking the activations of every image at almost the last layer, and it was a high dimensional vector for every image. So now if we forget about the images, these high dimensional vectors were being projected into 2 dimensions, and we were looking at that plot. So let's get to that. So first, visualizing activations, it just means which neurons fired and which neurons did not fire at let's say at the output of the first convolutional layer, which is a tensor. So that's why you have so many 2D maps. The second visualization was weights. Visualizations of weights make sense just at the first layer. Beyond that, it's not clear what the weights are doing because, for example, at some intermediate layer, your convolutional layer may not have just 3 channels or 3 as a depth, right? It will have, let's say, 10 or 100 as a depth. It's not clear how you're going to represent them. here actually they're just representing as grayscale, so it's not clear what's happening. So this is the third thing I was talking about, where you take the output of your convolutional neural network is mapping an image to a score vector, right? So ignore the score vector, go one level inside, which is the activations which feed into the score vector, right? In AlexNet, it happens to be a 4096 dimensional vector. So for every image, there's a 4096 dimensional vector, and now you ignore the images. You have this whole collection of 4096 dimensional vectors. You project them into 2 dimensions, and so let's say this is the board. You project all the vectors into 2 dimensions. Okay, so you'll get points, and you just replace the points with the images themselves. So that's the beautification of this particular plot. But that's what we mean by low dimensional embedding of the vectors. Okay, and then you kind of try to ponder what's happening. Are the representations good? So ideally, the representations are good if hopefully in the lower dimensional space, which is this 2-dimensional space, 2 images are close by if they have semantic relationship rather than just a pixel-based or color-based relationship, right? So if there's a blue car and a blue sky, hopefully they're not close to each other in this low-dimensional representation. Okay. So that, of course, critically relies on this projection operation being, having a good fidelity, in the sense it's maintaining some distance properties of these high-dimensional vectors in the 2-dimensional space as well, right? Another way to try to understand how the CNN's working is to try to look at, get an image. You have the trained network. Try to occlude a part of the image and try to see whether the probability of the correct class, how it's changing. And in this case, you can see that the probability of the correct class dips down to 0. Blue means a very low value, and red means a high value. So probability of the correct class is declining very much if you kind of occlude the face of the dog here. Okay. So it kind of gives an idea of what signals the CNN is picking to classify this input image as a dog. So here, for example, this part of the space is very important for it to classify this as the car wheel, right? And apparently, it's also picking up some other parts of the image. For example, this area and maybe this area, which is not related to the wheel, right? But it's needed for it to classify that as a car wheel. So if I occlude this region, right, that's corresponding to a blue region in the probability of the correct class. So here you can imagine that maybe in the database, in your database, you only had photos of wheels with the car, along with the car. You didn't have an individual photo of a wheel, and that's why it's kind of picking up these signals as an indicator for the car wheel, okay, label. And same thing, similar inference here as well. And another attempt to try to understand how the CNNs were doing was to try to start from a random image, pass it through your network, and try to pass it through the network and see which image activates a neuron the most. Okay, so you can actually pick any neuron. Let's say you can go all the way to the final layer and try to now the network parameters are fixed. The image parameters are now not fixed. So let's say if it's a CIFAR dataset, it's 32 cross 32 cross 3. Those are the number of variables. You wanna kind of update those variables. Those are your new W's, or you want to update those variables such that that neuron fires the most, right? So with that process, you can actually generate images. For example, if you pick a neuron at one of the top layers, you can and try to see which input pattern actually excites it the most. Then you can see that this is the pattern that excites it the most. Okay, one of the top layers, and at one of the bottommost layers, it will probably be just an edge or something like that, like a. So this was an attempt to try to understand what the neurons are picking up, what signals neurons are picking up to fire, right? If a neuron fires, as in its activation is high, that means it's detecting some pattern, right? So which image or which pattern at the input is going to make this neuron fire, give the highest activation was the question here. Yeah.
In this case, how do you know when to stop? Like when you are told that it is a boost or outbreak?
No. It's actually, I've just plotted two pictures. So you pick an arbitrary neuron. Okay, if you have a CNN, you pick an arbitrary neuron. Now you start from a random image and try to figure out, kind of keep modifying the image such that you get to some final image that excites this neuron the most. So random image may give that neuron's output to be 0. Now you see that, okay, the neuron's output 0, my target value is 1, so there's an error of 1 unit. You backpropagate that all the way to the image, make a delta change to the image according to gradient descent update, and again make a forward pass, look at the activation value, maybe it's 0.1, the error is 0.9, again backpropagate the error all the way to the image. That's what's happening here.
Okay.
Yeah.
So does that mean that, let's say here it's identified it as a ghost, right?
Yeah.
So there is a particular neuron that has learned to identify.
It hasn't identified, right? I mean, these are the patterns which excite that neuron the most, and you are kind of eyeballing and saying that, okay, this neuron is probably getting excited because of if it sees these types of patterns.
Okay. So in order to bring the image from this to this, every pixel has to be altered based on the backpropagated.
Yes. So it's like a weight matrix, right? The input image is also a tensor. A weight matrix is also typically going to be a tensor, right? So you can kind of freeze the rest of the variables in your CNN. All the parameters of your CNN, they are all frozen. Now the only variable is input image, which is a tensor. You just have to keep updating the tensor such that you kind of reach the objective value. So this is just again a nonlinear optimization problem. Optimizing for the parameters of the CNN was an optimization problem. Optimizing for the best image which excites a neuron is also an optimization problem. Yeah.
Why do you do it for a neuron and why don't we do it for the whole network?
You can do it for what do you mean? Which
image gives you the highest score for a particular case?
Yeah, that's what you can do. Let's say you picked. So you had a 1000-dimensional score vector at the end, right?
Yeah.
So let's say you want one of the scores to be highest and everything else to be 0. Then you try to figure out which image gives that one hot vector. So your target is 0, 0, 0, 1 coordinate 1 and all the other zeros.
Yeah.
Then you're asking which image gives me that all zeros 1 and all zeros, and these are the images. But you can pick any other neuron as well. I mean, it's not necessary that you have to pick the last one. Do you understand what I'm trying to say? Or what's your question?
You're saying it for one neuron, but I'm saying like according to a network, which image?
Which has lots of neurons, yes.
Yeah. So all these neurons finally give one score vector, right?
Yeah. It's according to the equations, right? The last layer, for example, in AlexNet is 4096 dimensional, which means that there are 4096 neurons at the last layer, which further get multiplied by weight matrix, and that gives the 10,000 dimensional score. So there's a W matrix at the end of AlexNet, right? In fact, there are two, but let's ignore that. So there's a 1000 cross 4096 weight matrix, but there are 4096 neurons here in the last fully connected layer of this network. Right? The outputs of these are multiplied by the weight matrix to get your score vector. So you can ask which input image maximizes one of my scores, or the normalized score, so that maximizing scores, since scores are unbounded, it doesn't make sense, but yeah.
So why are we asking this question? Are we asking people if the neural network was doing correctly, or is it just
during the training phase, you have an objective, which is to minimize the training loss or the validation loss, right? With that loss as the objective, you are trying to figure out the best parameters, right? In that feed forward, or not feed forward, but let's say with one hidden layer. If you remember lecture 1, with one hidden layer, this was the function, right? W2 times max of 0 and W1 times input plus bias plus another bias. So this was going to be my score, right? So there was an objective which was the cross entropy loss or the logistic loss, and we were just trying to change these W's so that we minimize the training error or validation error. Here we are not doing the same thing, right? Here we have been given a CNN, which means that these are fixed. B1, B2, these are all fixed. The thing which you want to change is X, such that let's say one coordinate of the score is high, or all coordinates of the score is high, and stuff like that. You can do any optimization, right? You can set for the training part the objective is fixed. Let's say cross entropy loss. Here I'm defining the objective to be change X, but that and figure out an X which gives me a score vector which is closest to a target score vector, right? You can take, let's say, mean square error type of error between the target score vector and the score vector generated by an X, and you want to keep changing X such that which meets the target, and the X which meets the target for, let's say, the goose coordinate being highest score, normalized score is this image. Okay. So it's not convincing. I mean, it's not very nice, right? Because this is not really a realistic image. You know, if you give a goose image, of course, you know, maybe the CNN classifies that image to be a goose, but the best image which makes the CNN classify that as a goose is this image, right? So, and this image was actually generated because of some priors being used. If you don't use priors, you even get very you know, they look like more closer to random noise than natural image. Any other questions? Okay, so let's now get to the content of today's lecture. So we're going to further pursue this idea of trying to optimize an image, to trigger certain neurons and so on. So which was the last part of visualization that we saw just now. So what do we know about CNNs? We know the following, okay, and it's somewhat intuitive from looking at the weights, the activations, which images fire the neurons the most, and so on. That each layer extracts features of increasing complexity, right? If you look at the first layer's weights, they look like edge detectors and so on, color detectors. If you look at the patterns, so here we saw the pattern at almost at the end. But if you look at if you pick a neuron, let's say in the 7th layer or the 5th layer, and try to see which image excites that neuron the most, you'll see that there will be some pattern. For example, there may be a circle which excites it the most, or presence of text which excites it the most, and so on. Okay, so first layer is looking for something very basic. Second layer, intermediate layers are looking for some components, and final layer is actually mashing up and trying to look for very complex things. And this part was what we visualized in a couple of slides ago. So let's now look at a couple of fun ways to further intuit what's happening. And the first thread is called Deep Dream. So what we do is following. Okay, we pick a layer and enhance what it detected, right? So what do I mean? So you pass an image up to some layer. So it can be even the final layer, but just think of it. You have stacks of layers, right? So pick a layer potentially. In this case, actually, the layer is picked very early, right? So you pick a layer, pass through an image, get the activation. So once you pass an image, at the output of every layer, there is an activation tensor, 3-dimensional object, right? Now you send them back via backpropagation. What do I mean by that? You assume that the activation values are the gradient values which need to be backpropagated. Okay. And once you backpropagate all the way to the input, here you're not backpropagating for changing the weights of the network. You're backpropagating to change the input itself. Remember the last thread that we were talking about, where the weights are fixed. You're only changing the image. Right here, this optimization. You want to change image or whatever input to get to a certain output. Here there is no objective. We forward pass the image up to a layer, get the activation tensor, and then send the activation tensor back through the layers and then modify the input. Okay. So this part should be clear. Like sending the activations back is because I'm doing backpropagation to modify the input itself, the image, which is what the thread we were talking about.
Is it like the applications like Prisma? Is it what the application?
Prisma,
As in
probably.
modifying the image?
Yeah,
The
yeah.
application is
No, the second thread we're going to look at is related to Prisma, I think. So this is just trying to understand what the CNNs do. That's the meta objective. But here we are trying to see what the let's say at a layer some neuron got excited. It has a high activation value. What it's trying to do is send that activation back as a gradient value, as a positive feedback, so that the next time I perturb this image, such that the next time the activation value will be even higher, some kind of a feedback loop, right? So here is just one pass. So we send it up to a layer and send the activations back and perturb the image. So this is the perturbed image. So it has some patterns that you see because certain activations were triggered. Certain activations were high and low. Those gradients change the image to something like this. Now, if you do that in a feedback loop for a long time, then some weird images come in. So the previous picture was for a lower level layer. So let's look at a high enough layer. So originally, actually, these images are from an original picture which had clouds. Okay. So what you do is the following again. Send the cloud image all the way to almost the last layer. Look at the activation tensors. Let's say this is the activation, right, before the scoring. This would be the activation vector, right, A vector. So send back the activation values as gradients, as initial gradients, as the candidates for gradients for that layer for which the activation was, and then you use the regular backpropagation to modify the image. You keep doing that over and over. You'll start looking. The image gets modified in ways where you start looking for new patterns which emerge in that image. So the patterns are these weird new objects. So the reason it's happening is, as I said, there's a positive feedback loop. A neuron which has a high activation value will try to send back a signal to change the image such that it still gets a positive value, right? So that's what's happening here. So maybe that neuron, maybe in clouds, for an image of of the sky, one of the score vectors which corresponds to the sky or the cloud should be 1. But you may have other neurons which trigger, for example, when a dog is detected or when a cat is detected and stuff. They also trigger, but they don't trigger to a very high score value, right? But they have a positive value. Now that positive value goes back to the image, gets fed back, and again tries to reinforce that positive value, and then you start getting images like this. Yeah.
What happens to the cloud value which is supposed to be 1 or the other one? Or is also measured?
Yeah, cloud will be there. If you look at the full image, we can try to. I can try to show you the full image in a second. So basically, so these images were generated based on this previous procedure. But now what you're trying to do is, let's say initially there was a huge image of a cloud or sky. Then you forward pass, get the activation values, send them back to modify that image. Now you kind of just zoom in on a part of the image. Now that is your new image. You forward pass that image, get the activation values, again send the activation values back, again zoom into a random part of the image, and do the same procedure. So the only change is you zoom into a picture into random regions of the picture in each iteration. Okay, so these were generated from I don't know what the base image was, but these were generated as outputs of this operation, and it's overlaid on top of another video, which is it's probably dreamlike, and that's why it's called Deep Dream. So you can actually get this code from Google's GitHub account. I actually ran it on my machine, but I'm not sure. We can look at the images later. Okay.
Professor,
Yeah.
exactly what is the objective of changing the input tensor? When we do
Yeah, we want to know for a neuron what's exciting it the most, right? So at the topmost layers, each neuron somehow kind of identifies a very complex pattern, right? In AlexNet, we have 1000 category, 1000 dimensional score vector. Before that, this A vector is 4096 dimensional, right? Now each of these 4096 neurons should fire. Let's say the input image is of a house. Then this neuron should capture the high level patterns of a house, not just at the element level, which the subsequent neurons will anyway try to fire, but this neuron should fire for the pattern of a house. These experiments are trying to see, okay, let me pick this neuron, and they're trying to ask what input image makes this fire the most. You can start from a randomly generated image, as in random pixel values. Let's say that input tensor, let's say 3-dimensional, right? Now you kind of keep changing that input image to figure out what is really exciting this neuron. You can always pass your training data and figure out which images are exciting this neuron. But here we are trying to synthetically generate the image which kind of excites this neuron.
So every time we change the activations, we are trying to maximize that activation value.
No, in these experiments, in this second set of experiments, there's no objective here. It's just an iterative procedure. It's like a random walk. Right? Every step I move left, move right with some probability, let's say bias probability, then eventually which region of this space will I be? Something like that. There's no objective in this iterative procedure. The previous visualization stuff that we saw in last lecture, there was an objective to maximize the activation value. Here, you pass an image, see the activation values, and then pass the activation values themselves as gradients. Instead of the gradients that you can actually compute, instead of those, you pass the activation values as gradients, as multipliers. So you kind of if the neuron fired more, then it's kind of sending a positive reinforcement signal that positive reinforcement signal which kind of activates it more.
Isn't it that in sort of objectives, which is there's no objective?
In this iterative procedure, no. Yeah.
Yeah. So isn't like what doing is somewhat taking the neuron and then trying to create an image out of it's like there is random pixel and trying to create a shape or an image, a perfect image that is exciting that neuron. So I can say that this neuron is being highlighted by a ship or a car.
Yes, that was the previous. That's what this was doing. Here in one iteration we are just getting activations, right? So you remember backpropagation. You start from the final. Let's say you pick a neuron. When you backpropagate the first neuron, the input is just 1, right? Gradient of the output with itself is 1, and then you multiply it with the local gradient, right? And then you propagate the gradients back. What I'm saying is, instead of sending back the value 1, instead of that 1 value, you actually send the magnitude of the activation. Instead of 1, it will be, if the activation is 10 units, then you send 10 units as the multiplier there. That's all. That's the iterative procedure here. There is no objective here. Is that?
Can we do a mapping that with every neuron we have that image which excites that neuron and then
Excites that neuron the most. When I say the most, then there is an objective, right? That's what this is. Which image makes that neuron fire the most, or makes that neuron's activation value the highest, are these images. And since there is an objective, you are trying to optimize the input such that that image fires, ensures that this neuron's activation is high. Right? Here we are not asking for anything. In one iteration, we are just saying pass an image to up to some layer, pick a neuron of that layer. You do the regular backpropagation to update the image, but while doing so, you start with the seed value, which is the activation value of that neuron.
What are we trying to understand?
These are some offstrings of the first one of the visualization threads that we saw. One of the ways to understand how the CNN is working is to see which image fires neuron the most, right? That was the objective of one of the threads in the previous section. Here we are just doing the same thing, but now we are trying to see which patterns kind of get enhanced. Let's say here I think they picked only up to, let's say, layer 2 CONV or something like that, and then they sent back the activations to kind of modify the image, which kind of improves those activation values. Then you see that the modifications are such that they are low-level patterns, some very simple patterns. But here, I think they went up to a very high layer, and that's why you see these complicated patterns.
So we are increasing the activation of the neuron and changing the image, right? Back and forth.
Yeah, we are changing the image. Yes. Yeah, that's the iterative procedure. Yeah.
So if you pass a, let's say, like you said, an image of the clouds, right?
Yeah.
So the network will try to impinge on the image what it's been trained on. It can't add anything new, right? So
yeah, if it's trained on some, so here you're seeing these things because
Are all
there are
animals.
lots of animals in the training data set. Yes. Yes. Yeah. So the second thread offshoot of this type of procedure is trying to look at image transformations. Okay, so we're gonna try to merge an image style onto another image. Okay, so this is your actually. I think this is the first time plotting this. This is the actual AlexNet. So I don't know if you can see the numbers, but so actually the image has a little bit of complexity because there are two. It seems like there are two tensors going on, two sequences of tensors, right? But you can just merge them together and just think of it as one tensor. Okay, each layer is one tensor. Okay, so you can see that the final score vector is 1000 dimensional, and the vector right before it, the previous vector, is 4096 dimensional. Okay, so this is the actual AlexNet from their paper. So what are we going to do here in this experiment is we're going to get an image. We're going to pass the image and get the activation vector. Okay, let's say the 4096 dimensional vector. Okay, here it's not related to them classifying it as anything, but let's just get an activation vector. We'll get another image. Okay, and we're going to again pass it through the CNN. Okay, and we're going to look at all the activations at every layer. And we're going to form something called the activation gram matrix. So how many of you know what a gram matrix is? Okay, a gram matrix is very simple. It's just the matrix of correlations actually. Okay, if you have two vectors, if you have two random vectors x, let's say it's d-dimensional, then it's just expectation of x transpose. Let's say there's zero mean. Okay. So this is going to be d cross d dimensional vector. Matrix. Where, for example, if you just expand x transpose, then it's x1 right? Expectation of x1 let's say, and so on. First entry. So an arbitrary entry will be expectation of xi xj, where x subscript I represents the ith coordinate of x. So gram matrix is nothing but a correlation matrix, right? If you had a d-dimensional vector, empirically, if you had many observations of d-dimensional vector, you know how to create correlation matrices. But just in theory, let's say you had a d-dimensional random vector, then this is the correlation matrix, right? I mean, if you ignore the, if you think of them as zero mean in each coordinate. So the gram matrix, just think of it as a statistic. Okay, we have a bunch of activations which are coming out of every so these are the outputs. Let's say at every layer, these are the tensors, right? And all I'm trying to do is create a statistic, which is, for example, something like correlation statistic. So I'm gonna do an inner product between the activation vectors. Okay, so here I have 4096 dimensional activation vector. So I'm gonna take an inner product with itself. It's a huge matrix, but it is a gram matrix. Okay, and then what I'm gonna do is now do an actual optimization procedure. I'm gonna optimize for an image. It's all about optimization of images. The parameters of your network are fixed. Okay. Now we're going to optimize for an image. such that now I'm going to define that objective. It matches the content of the first image and style of the second image. When I say matches the content, I'm talking about the activation vector. So, for example, I passed this image around, image through the network. I got an activation, right? The 4096 dimensional. I want to generate an image such that the activation values are close to this image at that last layer, let's say, and the gram matrices of the activations are close to this image's gram matrices. Okay. Two objectives. One is I want to generate an image such that its activation is close to the first image, and its functions of activation, which is the gram matrix, is just a function of activations, right? Functions of activation is close to this image's function of activations. That's all. Is that clear? If you do that optimization, you get something like this. Kind of gets the style from here and the content from here, and this is the image you can generate. I think on the lecture slide or the course website, I have put up a zip file which hopefully is self-contained, and you can execute something like this on your own set of images. There's a Python notebook for Python version 2 and a zip file which contains where you just need to execute a command to get these types of things. I think this is the one related to Preza or something like that. Right? Prisma. So this is, can you guys kind of identify what's the base image here? Okay. So this is from this repo. Okay. Actually, there have been publications on this. This is an image transformation task as recent as last year. So last year's ECCV, as a conference in computer vision, has a publication on this, doing this. Okay. So that was just for fun. So let's now focus back. We were trying to make an attempt to understand how CNNs work. Couple of embedding based method is somewhat sensible. Looking at weights is tough. Looking at activations is tough, but you can make sense out of it. I think in the last lecture we had I had a reference for DeepViz toolbox. You should look at its video to kind of understand how they are trying to interpret different layers of a CNN. Okay, there's a video link on last lecture's lecture notes. Have a look at it. So now let's come back to jump-starting CNNs. So very few people train a deep feed-forward network or a CNN from scratch. And the myth is that you really need a lot of data to use a deep neural network or even build a neural network, and we're going to kind of demystify it. So we will see two approaches if we have small data, and the first approach is called feature extraction, which is quite straightforward, and the second approach is straightforward. It's called fine-tuning, and both of these are loosely termed as transfer learning. So transfer learning is a branch of machine learning which tries to reuse models which are built on a different domain to try to reuse the models and build a model faster for a new domain. Okay, so it's a very industry relevant problem where, for example, if you have built a very hand engineered and spent a lot of time to build a classifier for predicting strokes, then can the same thing be used to predict some other ailment related to in the family of strokes or heart diseases? Okay, so that's called transfer learning, but we're gonna look at feature extraction and fine tuning to try to use small amount of data to get a deep network running. Okay, so what is feature extraction? So you get a pre-trained convolutional neural network, for example, a VGG network or an AlexNet that was trained on ImageNet. If you remember, I think I've shown AlexNet so many times. You remember that it was the winner for 2012 ImageNet challenge, right? Classification task. So the people who trained that network had 60 million parameters, and they have given those 60 million parameters as a file which you can download from the internet. So what do you do with feature extraction is you remove the last fully connected layer. For example, in AlexNet it's the 1000 dimensional score vector because it's the ImageNet problem. then you pass new training data. Then you pass new training data to get embeddings. When I say embeddings, it's just this activation vector. Okay. So what do I mean? So pictorially, let's say this was the CNN for which somebody spent days to figure out the parameters of the CNN, as in the parameters of the filters, parameters of pretty much the filters and the neurons here, the weights. Then you chop off the final fully connected layer, which is this the weight matrix here, which generates a score, right? And you pass your new training data to get what are called embeddings. So this is just the output of the penultimate hidden layer, which in this case is 4096 dimensional in AlexNet. Okay. I'm using the word activation vector, the representation of the image, or CNN code to all mean the same thing. It's just the output here, which then is linearly transformed to get the scores. Okay. So you get those embeddings, and then you just input these embeddings into a linear or a nonlinear classifier. So from that, once you get that 4096 dimensional vector, you ignore that you had images first of all. So you have just feature vectors which are 4096 dimensional, and you're just trying to construct a linear classifier and a nonlinear classifier. And you've already seen those classifiers in lecture 1. You already have scripts to actually build a linear or a nonlinear classifier, right? So you can just do that. That's what I've represented here as orange. So for example, ImageNet has 1000 dimensional score, so this matrix was 1000 cross 4096, right? Let's say for our data, for example, in CIFAR 10, there's only 10 classes. So maybe you want to build a linear classifier. Then you can just take the 4096 dimensional vectors for every image in your CIFAR 10 dataset, and then pass it through a linear classifier, for example, where the output score dimensional is just 2-dimensional. Let's say you are just, or in CIFAR 10 it's 10-dimensional, and cats versus dogs is 2-dimensional, right? Is the procedure clear for feature extraction? It's just you've been given a CNN, just get the activations, and then once you get the activations, it's just a regular classification pipeline, which you have seen in lecture 1. Any confusion here? Yeah.
So you are using the output of the last but one layer as an input to the next layer, which is next block, which is a classifier, which can be linear or nonlinear.
Yeah, it can be linear or nonlinear. Yes, correct. So that's it. That's the feature extraction way of standing on the shoulder of giants. As in, somebody has already built, has processed 1 million images and gotten you this, large-scale CNN, right? Like AlexNet or VGG or some other things that we'll see later on. You just reuse that to get features which are representative of that image. Okay, that is the operation being that's the operation happening here.
Professor?
Yeah.
So we cannot add more images if you want. If you want to add more images to train the data, train the network further.
Train this network.
Yeah, I mean, it's already trained network. If you want to add more images for, let's say for refinement, we can add it here.
You can. So first of all, you've just gotten the CNN, not the data which trained the CNN, right? You don't care about ImageNet data anymore. You've gotten the ImageNet CNN. All you're working with is your own data for now. Now with your own data, you can just stack on another classifier which takes this 4096 dimensional vector as an input and train the parameters of that classifier, whether it's linear or non-linear, that you can do. Yeah.
So does that mean that we can have different images which the original thing was not trained on?
Yes. That's what we are doing, right? Here I have not constrained you yet. So you can say ImageNet was trained on so many thousand categories. I'm gonna pick some other category, right? Some other classification task.
For example, this parameter from the first network were actually trained for the original image.
Yeah.
Now, for example, like he asked the question.
Yeah.
You are impinging a new image here now.
Yes.
And the old ones you are not changing.
Yes. Old image-based network parameters that we learned, the weights, that is not changing. So how does it work? There is a there is a slide to I'll answer that question in a minute. Okay.
Are we changing the parameters in the original? We are not changing that.
We can. So in feature extraction based thread we are not. In the next thread, which is this fine tuning, we are. Okay. So what does fine tuning do? Here we retrain or fine tune additional layers of the pre-trained network if we have more data. So it's basically just saying, okay, instead of taking the 4096 dimensional vector, let me take some other tensor in between. That is the representation of the image. And all the other layers, if I keep the network structure, then I can actually do backpropagation that part, right? My input will be that input tensor. It's not the image here. Whatever is the input tensor here, let's say the output of the pool operation. Then I can train, let's say, 2 fully connected layers, which is going to be nonlinear function. Let's say with some nonlinearity here. I'm going to train, I'm going to backpropagate and change the weights. So let's say this was the original network. I chopped off the final thing because it is anyway a 1000 dimensional, this matrix which is giving me a 1000 dimensional vector. I removed it anyway. Let's say I have a 2-dimensional output, cats versus dogs, so 2 outputs. So that's this fully connected layer. Let's say I don't want to, I want to keep the same network structure, but I want to not use the same weight. So I can actually backpropagate up to this point, let's say. Freeze all these weights. So it's as good as saying, take every input image in your new training data, get this vector, and then ignore the rest of the thing anyway, and then just do backpropagate on this part. That's what it is. You can go all the way back actually. If you have lots and lots of data, you can retrain everything. In fact, at the one end of the spectrum, you can ignore all the weights. So it's as good as saying, I don't want to take in the pre-trained CNN. I'm going to have the CNN structure, and I'm going to retrain all the weights for your new data set. If you had lots and lots of data set, lots and lots of training examples. Yeah.
Can you go to the previous slide? So the more specific features are the only ones you technically need to train. Right?
Yeah, ideally you want to retrain them if you had for your new domain. Ideally you want to retrain them, and these turn out to be, as you saw, for example, here it's basically filters, edge detectors, and things like that. So there is no need to train, no need to spend your training data effort to figure out those edge detectors again. Okay. And the benefit of transfer is immense actually. So we can get significant boost in performance compared to hand engineered classification or machine learning pipelines. So for example, if like AlexNet pre-trained CNN is available, Google's GoogleNet CNN is available online, same with Microsoft's CNN as well. So these are winners of the ImageNet challenge. You can just use them to get the feature vectors up to whatever layer you feel like, and then maybe do an SVM, do a feed-forward neural network there, and so on. You will get a boost in terms of performance compared to whatever traditional method you are doing by hand engineering for your small domain. Okay, and these guys from I think mid 2014, they show performance compared to the best state of the art of a traditional pipeline versus the boost that they got. They did not even train the CNN, right? They just got the CNN and just solved the SVM problem. Okay, and they're showing the performance. So it's not exactly very clear. So I think the hollow box. So green is the previous this pipeline, and the hollow box right next to the green is the performance of an off-the-shelf pre-trained CNN. Okay, so it's not always the best, right? It's worse a little bit, but you're almost getting the same performance as the best state of the art.
So if you're not doing any transformation in the network, it has to be a subset of the original data or something.
It doesn't have to be a subset. So that's what I'm going to comment on in a slide. Okay. So just an aside. So what do all these things mean? Object classification. That's what we saw. That's what we've been looking at. There are a lot of other topics in vision based machine learning, right? So some topics, example topics are given here. So this was the classification task. There are tasks like classification and localization where you need to your machine learning pipeline system has to also generate the bounding box of that of that input image. Where is that object that you're detecting? Okay. here you need to actually detect, so this task is called object detection, where you will have multiple, potentially multiple objects, so you need to tag all of them and give the bounding box for all of them. And image segmentation is the task of actually giving the boundary, the contours, which separate that object from the rest of the image, from the background. Okay. So these are some of the tasks. So there are a lot of other tasks like scene classification and so on, but just an example of few other tasks. So when to actually transfer? Okay. So if you have a similar data set, it need not be actually a subset, but let's say, for example, there's one data set that we are looking at in assignment 1, which is cats versus dogs, right? So it happens in that in ImageNet there are lots of cats and dogs subcategories. It's not exactly the out of the 1000-dimensional score vector. I think multiple categories are just some subtypes of dogs. Okay, like the Pomeranian versus Yorkshire Terrier versus something else. So there it's not exactly a subset, but the new task has almost the same images, same types of images as what ImageNet based CNN saw. So there you're in really good shape. So you don't really need a lot of new cats and dogs pictures to figure out a classifier which can differentiate between cat and dog, let's say. So if you have similar data sets, you can do these, but it's an extremely different data set. Let's say like ImageNet has no data or no category related to medical images, let's say. Okay. In that case, and you want to do some classification on MRIs directly detect regions of cancer, or whether you have a malignant tissue or a non-malignant benign tissue or something like that, then it's going to be a different data set. Try to see if you can reuse the lower level layers of the CNN, as in outputs of the lower level layers. Whatever is the tensor, that's the input for your next classifier. But if you have a lot of data, then you're okay, because you can fine tune a lot. You can pretty much start with that weights as the initialization weights of that architecture, and just keep full backpropagation to get new weights. So it's as good as saying I'm just going to start the network with those weights trained from ImageNet, but then I'm going to keep updating those weights because I have new data. Okay. So I hope this answers your question, because it's a subjective matter which the designer has to decide whether the image domain that you have is actually transferable or not. Like if it's completely untransferable, let's say you train in CNN on just astronomical objects, it's just pictures of stars and trying to classify whether there is a star or not, and you want to use that for cats versus dogs, probably it won't work. So how to transfer? There are lots of pre-trained models available, as I was saying. There are TensorFlow models. There's Keras also has a bunch of models, and Caffe, which was the I guess a somewhat older software system, they also have a lot of these state-of-the-art CNNs, at least, that you can use, and they're not restricted. And these models can be used, as I said, the CNN features can be used not just for classification tasks, as you saw in 2 slides ago. They're used for a lot of other things like localization, object detection, and so on. So, and this is going to be key for your projects as well. So, one network which is kind of clean enough that I can talk about it today, because it's almost the same thing. It's based on the principles that we saw in the last lecture, is the VGG network. VGG just stands for Visual Geometric Group. It's a research lab, I think, from Oxford. So they ranked second in the 2014 classification challenge, and they used 3x3 convolution filters with stride of 1, where the depth of the filter is just dependent on the input, right? The number of filters and all that I've not written here. They use ReLU nonlinearities, and they have 5 pool layers, which you can see here. This actually I got from their one of their presentation, and they have 3 fully connected layers here. So actually this network is available. The weights are available that you can download and run the model and classify an example image. For example, you have an example image of a cat. You want to actually see whether the trained network classifies it as a cat or not. You can do that. I was going to demo it, but I have some issues with my Python, so I'm not going to demo it today. But this is pretty much all the layers you should be familiar with. You know what? I guess minus -64 just means 64 set size is 64. Okay, the number of filters is 64. All the filters are 3 × 3 in terms of the spatial dimension. So for example, here the depth is going to be 64. So the tensor size is going to be 64, and I mean depending on the image and the 3 × 3, there will be a space. What is that? Height and width number here, but the depth is going to be 64 dimensional. Is that clear? Okay. So next we're going to look at neural nets in practice. So we're going to revisit a couple of things. From first lecture, if you remember, I had structured it as 4 topics, right? In a classification pipeline, you kind of want to think about the data, you want to think about your model you're going to use, you want to think about the loss function, and you want to think about the optimization technique. Okay. So here we're going to revisit these two of those threads, which is data and the models. Loss function, we kind of have already seen that they're typically cross entropy loss, the softmax loss that you've seen, or the logistic, or the SVM loss. So we are not going to discuss loss functions, but we're going to discuss data and models. So there are a few empirically validated techniques that improve the performance, the classification accuracy of these networks, and we're going to specifically look at something called data augmentation on the data side, and on the model side we're going to look at how to initialize the weights, and a couple of other tricks that you might have heard keywords of. I don't know if you've heard of dropout, so we're going to visit something called dropout. Okay. For our discussion, we're going to fix the optimization technique to be a gradient descent based method, so just the batch stochastic gradient descent that we have seen, and we'll revisit the if we can make any improvements to the gradient descent method itself later on. Okay, so let's look at augmenting data. So this is what you do with your data set, right? You have your data, you pass it, do a forward pass, and you compute the loss value. Sorry, actually slide mismatch. So what are we trying to look at here in the data part? So we want to look at how is data handled for these deep neural networks. Okay, so what is the difference? What is the difference from the regular pipeline? So how is the data handled and what is its quality? These are typical questions that you may have in terms of implementation. In terms of handling, deep nets may need to read a lot of data sets, right? If you really want to train a convolutional neural network using ImageNet data, that's 1.4 million images, right? So if you want to read that from disk, your disk better be a good hard disk, right? It hopefully is a solid state drive maybe, but even if it's a hard disk, keep them in contiguous spaces. So that doesn't happen if you just copy paste your images. Okay. In terms of quality, you ideally do want to collect as much clean data as possible, but there's always a trade-off between the data that you collect and sometimes the unclean data that you have. So you may not want to expend time or other resources to collect more clean data. Then you may just want to work with unclean data. Okay. Now we're going to try to see, okay, these are some issues that will come up, but let's say we have a data set, it may be clean or unclean. Now how do we extract the most out of this data set to either feature extract from my pre-trained CNN or train a CNN from scratch or do the fine tuning? How do I do that? So in terms of the data perspective, we can do one thing, okay. We anyway, if for an example we we're going to use it to compute the loss Li and so on and do backpropagation, right? Let's say in a batch, we're going to now create an augmented data. As in, for an example I'm going to create new copies of the same example where I'll change the input. Okay, so I'll have an x tilde I instead of an xi, where x tilde I is a function of xi. Okay, sorry, there's a typo there. Where x tilde I is just a transformed version of xi. So what do you think this could be? I'm trying to create new data. So let's say I have a data set which has 100 images of cat, 50 are of cat, 50 are of a dog. I'm trying to create additional data with the same data set.
It's similar to the activation, whichever is activated.
It's not even that complicated. I'm just looking at I have my data set which is just 100 in number. So I'm going to do the following, which is very trivial. We just change the input without changing the label. That's what I said. When I said if I have an xi yi pair, I'm going to generate x tilde I yi pair. So a label is the same. So what I'm going to do is just kind of do transformations on those images, right? This is specific to image data. You can't do this arbitrarily for, let's say, your numerical data. You could add jitter to your continuous data examples, for example, continuous features, for example. So let's say, I'm just making some transformations like flipping the image, changing the colors or the color contrast, doing a random crop, random rescaling, and so on, and use these as again new data points, right? Instead of xi, these are x tilde I. Okay. And it's actually surprisingly a very widely used technique, at least in vision. So you really need to extract the structure of your data. And at test time, what do? You can actually figure out. You can actually take average of predictions of fixed set of transformations. You can actually not just pass the test image through your CNN and get a label. You can actually again do the same operations like crop the image, take a change the color a little bit, and try to guess the labels, and take maybe the average of the weighted majority of the labels that your network is guessing. Is that clear or no? So I'm just saying that if you had an image, so training is clear, right? I had a data set with, let's say, x1, y1, x2, y2, x3, y3. I'm just creating an additional augmented data set which is x1 tilde, x1, okay, let's call it x1a, x1b, x1c, where a is, let's say, the top half of the image, x1b is the bottom half of the image, x1c is the changed color image, and the same label. Now this is my huge data set. I just multiplied my data set by 3 times, right? If I do that for every example, I just got a 3x bigger data set. So this is clear that with this data set, I'm going to train my network, as in I'll set the weights of my CNN or feed forward neural network. At test time, what will I do? I'll have an x subscript test, right? I can always pass this to get a label y subscript test or predicted label, right? I'm gonna again actually not just get that, I can also crop this image, right? Crop this image and try to make a prediction. Change the color and try to make a prediction. I'll get a bunch of predictions. I can take the average or let's say weighted majority. That's all I mean. Is that it's very straightforward. Is that clear? Yeah.
It's all of time, but won't flip confuse the network?
So maybe here it will confuse the network. It's a bad example, but for a cat or a dog, it's a symmetric, ideally.
Yeah, or a car, I mean, if you flip it will.
Flip is basically trying to change the viewpoint of the camera or whatever captured that image. For this, probably it's a bad example because it's text in there. For a car, it should not be. Oh,
If you flip vertically or horizontally.
I think I only did a mirror flip. Yeah. So actually, this technique, actually there is no set of procedures. This data augmentation thing, you can do all creative things, whatever you want to do. In fact, one subthread in your project can be, I have a data set, I'll create my own transformations and see whether the augmented data set is giving me a performance boost or not. One subthread can be that. For example, this a particular network, I'm just gonna bring up names here, but ResNet is the 2015 winner from Microsoft. Okay, So what it did was it scaled the image at 5 different scales and then predicted. Okay, so if you give an input image, it's going to scale it to 224 cross 224, 256 cross 256, 384 cross 384, all these 5 scales. For each of the 5 scales, it's going to do 10 crops of the image. As in, it's going to take the top 224 cross 224, the top left, top right, bottom right, as center. Okay. Remember, ImageNet is actually all the ImageNet images are 224 cross 224. So for any other image, how are you going to work with them? You're going to take crops. But what I'm trying to say is that these guys did data augmentation of the ImageNet data anyway, which I'm not sure if they've disclosed or not. But for the test image, they are saying that we're going to do all these crops. So basically, for each flip, I'm going to do 5 crops. So that's why they have 10 crops. And do that for every scale of the image and get the predictions and take the average prediction. It's just trying to robustify your network's prediction. Other ways to augment data include changing the contrast color. You can also do translations, right? If you have a cat in the center of the picture, you may want to move it to the left and the right, and hopefully the networks will still output the cat score to be higher than all the other class scores. Okay, so these are all regular transformations that you can do, and these are all specific to the image domain. Okay, and this is very so small data sets. From one point of view, you can think of this as adding noise, because a transformation is not exactly a noise, but from a point of view, you can think of it as I had an original data. I'm adding noise to it. Think of your regular linear regression that you would do with numerical data. If you add a little bit of noise to each of the column, a similar operation is being done here, but it's exploiting the structure of the image. Right? That's the only difference. And this averaging of a lot of predictions over cropped or variations of that test image and then taking an average is essentially like marginalizing out the noise. Taking a weighted majority kind of shrinks the noisy outcomes, right? Okay. So in terms of, so that was the data part. So there's not much going on in terms of data. We revisited the data part and we saw that we can augment our data. In terms of model, we've already seen a few things that we could tweak around. First thing was the choice of activation function. We said sigmoids are not that good. Maybe tanish are not that good. ReLU and variance. Okay, we looked at them. We also looked at, okay, there's going to be this choice of the number of layers and the number of neurons per layer, which totally depends on not just the classification accuracy or whatever the task accuracy that you're doing, but also depends on your computation power. Okay, for example, VGG net that we have not seen has 160 million parameters. AlexNet has 60 million parameters. So to kind of update all these numbers, so at every iteration gradient update you're doing, you have 160 million numbers and you're perturbing those 160 million numbers, okay, which is a lot of numbers. So those choices you did, and you also did filter choices like how big should the filter size be? Should it be 3x3 versus 5x5? Those are all design choices. We're going to look at some other choices while training these networks, which actually make a difference in terms of performance accuracy. These are some new topics. Something called, first of all, first thing is straightforward. It is just weight initialization. Should you set all your initial parameters of your network to be 0, non-zero? What should it be? Second thing is something called batch normalization, and third thing is something called dropout. So we're gonna kind of look at these three in a little bit more detail after a small break, 2 minutes. Yeah,
You remember this non-MSP student?
Oh yes. What happened?
So I'm still like, just come to your lectures.
Okay.
So like, what I wanted to ask is, so transfer. I know the principles.
There's a lot of.
I
It's
know.
just some basic thing that.
Yeah. So the thing is, I was working on a different project actually. It's on breast cancer using mammograms.
Yes.
That's very wide project. So
Yeah.
what I was doing is I had like 30,000 images.
Mm-hmm.
So actually I just have 990 images. So I have this in my data set.
Yeah.
So and the sizes are too big. So it's like 2,000 cross 2,000 images, right?
Mm-hmm.
So what I did was I cropped the images to 24 cross 2,000 from these 2,000 cross 2,000.
Yeah.
And according to the tumor location that I already have as a label,
Mm-hmm.
I saw if this 224 cross 2,000 image overlaps with the tumor location, then I'm labeling it as a tumor, be it benign or be it malignant. And if it's not, then I'm labeling it as normal.
Yeah, sure.
So from this 1,000 images, I've got this 30,000 224 patches.
Yeah.
Right?
Yeah.
For 3 classes.
Yeah.
Now, this was for the data.
Yeah.
Now, I was using a simple CNN model with three CNN layers and 3 fully connected layers. Like, I'm not getting a good accuracy for this.
Okay.
I had 2 things in mind. First, maybe my data set is not too big, which I think I can overcome by using augmentation. But the rotational stuff that you mentioned, I don't think personally that those matter for CNN because even if you translate a cat image, if neuron 1 was firing for a particular position, if you translate the neuron 2 will fire. It's just the pooling that we do. I think that takes into account these translations. I don't think for my project that would be of much use. I just wanted to ask you because I don't think using a pre-trained image and all would help in medical imaging, like you mentioned.
You can try though, because it's just forward passing, right, to get feature vectors.
But the edges and stuff I understand. Those will be same. But the detailed specific features, because in a CNN model, once you go into the specific feature, you get the eyes, you get the faces. I don't think those will be useful.
Yeah, they may not be. Actually, that's why visualizing what happens at each layer, how many activations are getting fired, are there dead, are there dead neurons which never fire, all that stuff you need to kind of debug. We can take this offline, or tomorrow I have an office hour to you can. 3 to 5.
Okay, so I'll ask the students.
Okay.
I don't know personally. I don't get the emails actually.
Sure.
I'll ask them.
Okay, yeah.
And I got it out in assignment for fourth part of the question. It says to calculate the loss functions, right? Logistic loss and L2 regularization. Does it mean same as the regularization loss that you mentioned in one of the examples?
L2 regularization, so, same expression. Sum of the squares of the each entries,
You've given a sample code in the slides, right?
Yes.
So it's something similar like that?
Yeah, same thing.
Okay. And the summation is called actually cross entropy, average cross entropy.
Yes.
So it's all the same.
Softmax is the same as cross entropy.
Data loss.
Softmax loss, cross entropy loss, logistic loss is all the same thing.
Okay.
SVM is different, but those expressions are there already. Regularization is different. L1 and L2 just mean sum of the squares of the entries or sum of the absolute value of the entries. You remember one of the slides in lecture? Yeah.
So L2 regularization happened, but the regularization loss.
Yes. Regularization number, but that gets added to the loss. Yes.
So final loss, we have to sum up the data loss and the regularization loss, and then try to see that it's minimum.
Yes.
By changing the learning rates, right? Like
you're going to do gradient descent. One of the parameters in the gradient descent is going to be the learning rate. If you change the learning rate, what happens? It's a function of iterations. Okay.
Yes.
Yes.
Simple question. We are now doing a project for the morning star.
Morning star.
Yeah. That's an assignment for our capstone course.
Mm-hmm.
Yeah, and now our object is to classify the files from many files. Basically, we need to classify each file to one kind and not this kind.
Files, they are not images.
Files, not images.
Okay.
So do you think deep learning will help to this classification?
Yeah, why not? I mean, but not CNNs. You may want to try the feed-forward neural network. The thing we saw in lecture 1, feed-forward networks.
Feed-forward?
Yeah, everything is collected to everything in every layer.
Okay.
Yeah. So you in the assignment also as well as in the example scripts, we had a linear classifier and a one hidden layer classifier, right? So instead of one hidden layer, you can have multiple hidden layers. That's a feed-forward, fully connected deep network. You can make a deep network and see whether that helps.
So how about the RNN network? How about the RNN?
Oh yeah, RNN we're going to discuss next class. You can see it is useful for text data, but I'm not sure if your files is all of text, is it?
Files
okay.
All texts.
Yeah, so maybe next class is going to help you. We'll see. Yeah.
Do you have any suggestion for the because the documents, the files are unstructured data. So do you have any suggestion for us about how to transfer the documents to the numerical features?
Yeah, we have. That's what we're going to look at RNNs and something called word embeddings. So it will be numbers eventually. It will not be just characters, whatever strings or words. It will be numerical features. We'll see next class.
Next class. Okay. Thank you.
Okay, so we're going to resume. Okay, let's look at the first, guys. We'll resume the lecture. So, as I said, we're going to look at three threads here in terms of models. In terms of data, we said, okay, let's augment the data. We can work with CNNs. Now, in terms of models, there are a couple of key techniques which have emerged empirically, I would say, that one may need to know about. The two techniques are batch normalization and dropout. And the first thing is just how do you start with the weights? If you're going to do an optimization procedure, you need to start with an initial model, right? So, what is the weights of that model? So, weight initialization actually plays a very, very key role in training deep networks. In fact, it can make or break deep networks in the sense that the development that you saw in 2012 when the AlexNet actually beat the previous hand-engineered pipeline to classify images, they actually had to take a lot of care to get their images right. Otherwise, their performance would be quite bad, and that's very naively because it's a very non-linear landscape of the loss function. If you can imagine a loss function, just think of it as in the 3D plane, although it's not a 3D loss function. In the 3D plane, I just mean that in the three-dimensional space, I just mean that the loss function is just parameter of two parameters, right? You can just have a plane on which you can vary parameters. Let's say it's A and B, and you can see how the loss function looks like. It may look like some kind of a 3D surface with lots of minimas, hills over here, valleys somewhere else, and so on, right? That's in 3 dimensions, but in very high dimensions, the loss landscape has lots of ups and downs. That's what I mean by non-linear. So weight initialization is very key because you may get stuck in one of these local minimas. That's the picture I've shown here, where let's say you want to minimize the loss function here, you want to get to this point, and so where you start kind of determines where you land, right? If you're going to do gradient descent, start from here. The gradient direction would say that go right. Okay, so this is a one-dimensional, let's say one-dimensional, one parameter, and this is a loss function. If the loss function is nonlinear, if you start from here, the gradient direction would say, negative of the gradient would say go in this direction, and so you will end up at this point. Okay. Is that clear? I mean, because actually when you do assignment question number 2, hopefully you'll get some intuition about this. Okay. So let's say, let's pick one example. Would there be any issue if I set all my weights of my neural network to be 0 and start my optimization procedure? What is the issue?
Max will always be 0.
What will always be 0?
If you use ReLU, then it will always be 0 and it will always continue in that.
Yeah, yeah. So as I said, if I use ReLU nonlinearity, then it's a gate which doesn't pass back the gradient if the if its activation is 0. So if all the weights are 0 at every input of every neuron, then the output is going to be 0 unless the bias is positive and stuff. So there is some issues with weights being 0, but it's not. But let's say we set some other weights. It's not just the issue of local optima that I was projecting here in the beginning of the slide. I'm saying that where you start also kind of influences how the gradients look like subsequently. That's obvious, right? If I start here, the gradient is has some slope here. Maybe if I started here, gradient has very high slope. Things like that, right? But the starting point also influences the magnitudes of the gradients in the backprop. So, which essentially mean the activation statistics influence the gradients. So, if you start at some W or some set of initial weights, you pass your let's say some part of your training data to compute loss, right? L value, and then you want to compute the gradient such that you can update your weights. That's what is a backprop thing, right? When you do the forward pass, because I set some weights, those activation statistics are functions of those weights, initial weights, right? Now, based on the activation statistics, my backward pass is modulated by that. As I was saying, if ReLU is off, then the gradients won't pass through, right? So the activation statistics, which depend on the initial weight that you set or initial parameter value that you set, kind of influence the first set of gradients that you get back to update your weights, right? And so it may end up that none of the none of the activations or none of the ReLUs are positive. For example, when weights are 0 and bias is 0, then the ReLU's output is 0 and input and no gradient is passed. The loss number will be some positive number, let's say. Then that loss number will not be passed back all the way to the parameters to update the parameters in the gradient descent algorithm. Okay. So there are some heuristics available to kind of take care of how to not set it to 0, how to set it, right? So if one straightforward thing you can do is for every weight value, as I said, let's say AlexNet has 60 million numbers. All these are weights or biases. I can set I can pick do a for loop and get each number to be a random number between, let's say, 0 to 1 or -1 to 1 or something like that, right? I can do that. That's random initialization. That's better than doing setting all of them to be 0, let's say. But people have observed that even that is probably not good enough. It's not. It's a tricky problem because depending on the data set and the initial weights, your initial activations. As I said, activations are functions of weights and initial data set. So just random initialization may also not be good enough, and so some research papers in the past 2-3 years have tried to figure out what should be the right way to initialize these weights. Okay, so from this slide, I just want the takeaway point is that weight initialization kind of may heavily influence the performance of your trained network, whether it's a 2-layered feed-forward network or a multi-layer or very deep feed-forward network or a very deep CNN. Weight initialization is very important. So if you're going to build a feed-forward network or a CNN, then you better take care of how initial weights are influencing your search. One look, if the gradients all all good, still you may be stuck in local optima, but it could be that because of the way you're trying to compute gradients, they may not even be backward propagated. That's the second issue. To somewhat kind of ameliorate this issue, there's this technique called Bash normalization. So, as I said in the previous slide, activation magnitudes and the statistics depend on the dataset, the network, and the nonlinearity used. When I say the network, I'm talking about the parameters of the network. Okay, and these activations influence the gradient propagation and hence also learning, in the sense that the activation value typically gets multiplied to the invert gradient. The activation value of the previous layer gets multiplied to the gradient that's coming through a node. You can actually, if you have gone through the example scripts from lecture 1 or week 1, you remember that so if you look at the script, inspect the script carefully, you will see that for the fully connected neuron, the whatever is the gradient here, when you backpropagate, you actually multiply the gradient with the activations. So these x's, for example, if it's a layer in between, the x's are just the outputs of the previous layer, so those are also activations. So your gradient gets multiplied with the activations of the previous layer, right? And that's how activations influence the gradient propagation as you go all the way back to the weights of the initial layer and so on. So the question is, so the question being asked in this solution approach to kind of deal with this weights and gradient propagation issue is that, is there a way to control these activation magnitudes and their statistics? Okay, if I can somehow manage to control these activation values and statistics, then maybe I can get the gradients to propagate really well. Okay, and the way we control these magnitudes and statistics is by something called Bash normalization, and the idea is very, very straightforward. The idea is to make each activation unit Gaussian by subtracting the mean and then dividing by the standard deviation. So you have a random variable, you subtract, let's say it's a non-zero mean Gaussian, so it's not a unit Gaussian. By unit Gaussian we just mean that the mean is 0 and the variance is 1. Okay, so let's say it's a different it's a random variable which is taking a which has a mean centered 5 and a standard deviation of 10. Then you know how to normalize it, right? You can subtract the mean and divide by the square root of the variance, then that new random variable is going to be a unit Gaussian. So what we are going to do is, at the output of each layer there's going to be the activation, right? You have an activation tensor actually, but you can look at one coordinate of it and it's an activation, right? What we are going to attempt to do is try to change that activation value. So let's say I have D filters, okay, and I'm also tying it with something called a batch, okay, because if you remember in lecture 0 we said we're going to do gradient descent. We're not going to, when we do gradient descent, we're not going to forward pass the whole data set to compute the loss number, right? Ideally the whole data set is used to compute the L, right? Li, you're summing over all the data set. But instead of that, if I have 1.4 million images or dataset entries or examples, I'm going to take a batch of 100 images or 200 images and only compute L with respect to those 100 images. So let N be that number. Okay, so that's called a batch. And let's say I'm at the first convolution layer of I'm at the first convolution layer of AlexNet. So the first convolution layer I think has 96 filters or 64 filters or something like that. So then D is going to be 64 or 96. So let D be the number of filters and N is the number of images that you're considering right now for your forward pass. Okay. Then I'm just representing by a matrix all the activations, right? So there are n rows here. So each row is just the filter output. Is just the output of each of the filters. Okay. So if you think of the do you have that image? I don't have that image. If you remember the 3D picture I had drawn before, there was a slice I had picked out, right? It was a depth slice, right? There was a depth slice, right? There was all these neurons have the same filter associated with the same filter. Instead of the depth slice, I'm now looking at this. This is the depth. Actually, there's a technical term for it. It's called a fiber, but you can just think of it as, let me look at one row of the neuron activation, so a row of neurons which are all looking at the same receptor field or same input area. Okay, input tensor will have some spatial region, right? So I'm looking at the same thing. Across the filters, there will be a bunch of neurons which are all looking at the same thing, right? So those are the entries of this row. Yeah. So there are D filters. So there are D neurons here. It's the orthogonal direction to the depth slice. So there are D neurons here. There are D numbers, and N is just I'm just aggregating N numbers for each of my training examples in my batch. So if my batch is 100, then it's 100. Okay. So this is my original data. By batch normalization, all I'm trying to do is I'm going to take column by column of this matrix and just do this simple transformation. Okay. I'm going to take the average of this column, that's E of x. I'm going to take the variance of this column, that's variance of x. And then let's say there are two parameters, gamma and beta. And then I'll get a new column. So it's entry wise, I'll get a new column. Right? That's x hat. I'll have the n cross v. And that's it. That's the input to output transformation for each each slice which is orthogonal to the depth slice. So actually not each slice but each fiber. Okay. So this is just a computational procedure that I'm now defining. That okay, I have a output of my CNN. It's a 3D volume or 3D array. I'm going to pick one thread like this, or it's called a fiber. But I'm going to pick a fiber across the batch. I'm going to do an averaging and get the variance, and then I'm going to remove the mean and normalize with the variance. It's just a regular operation. These two numbers are parameters of that operation. Okay. You can see that this is a differentiable function. So if I can do this operation between my layers, then I should have no issue with backpropagation. Okay. And also at test time, there is no concept of batch because I'll just have one image, right? So at test time, I will not have these expectation of x and variance of x because I will not have a batch. Then I can just use the training data means and variances. That's just a hack between training and test. But otherwise, I can get these expectation of x and variance of x, right? So what does it actually look like? So previously I had this, let's say I had this neural net, right? It need not have con pool, it can even be fully connected network. Now I'm just inserting a batch normalization layer between the con and the nonlinearity. So previously I used to couple the nonlinearity with the con layer because it's not really doing much except for adding nonlinearity element wise. All I'm saying is I'm going to insert a batch normalization and then do the nonlinearity before going to the pool. So these are the additional operations that are happening.
The fiber which you were saying, it is nothing but the number of filters which we say in CONV.
Yeah, so this D is the number of filters, yes. Yeah. But you do this operation like you do this operation at height times let's say width. So those many operations, those many matrices you will have, right? Because of the batch. Batch is just adding one additional dimension. That's all.
Isn't the column of the filter like you have the slice that you cut, isn't that the filter?
This is the depth slice for a single filter. This one, this slice of the tensor, that if you remember from slides, I don't have that particular picture here, but if you remember in the output of the convolution layer, one slice or one 2D map was related to just one filter. There will be so many neurons, which is width times height, but all the neurons are associated with just one filter or one filter weights, one set of filter, one collection of filter weights, right? The 3D tensor, 3 cross 3 cross, let's say depth or something like that, input depth. So what I'm saying is I'm not looking at, so this B is not related to one filter, this is all the filters, but I'm looking at all the neurons looking at the same receptive field or the same input region of my input tensor. Yeah.
So the aim of doing this is to actually multiply the gradient when it's going back, not about the forward activation.
No, it's all about forward operation, right? I mean, it is a part, it's a layer in your, I've modified the layer, so if you do a forward pass, it will get transformed. If I do a backward pass, it will also get transformed. As long as it's not an identity layer, it will get transformed, right?
But you're applying this over a batch of 100.
Yeah, I'll see. When I do a forward pass, typically people do a forward pass not example by example. They'll bunch. Ideally, in really ideal situation, you have to do a forward pass with all your training data, right? All your training data has to be forward passed to get the loss value. Typically, what people do for one gradient descent iteration is they'll just take a batch of 100 images and just do a forward pass. They'll actually do that forward pass together because it's all matrix operations going on.
When you said together,
Together means you don't have to like call, you don't have to compute the when you're doing a computation, right? You don't have to compute it image by image. You can stack n images together and do the matrix multiplications all at the same time. Or when I say do a forward pass, it's a bunch of matrix multiplications, right? Like at conv layer, it's a bunch of matrix multiplications. We'll actually see the matrix multiplication again. But when I say a forward pass, it's all the operations which involve multiplying the filter with the elements of the filter with the elements of the input tensor, pass through the nonlinearity, do the max pooling, again do the filter to input tensor element wise multiplication. Those are the operations, right? That's what I mean by forward pass. That you need to. Last lecture we saw that we did that for one image. We don't have to do that for one image. We can do it for multiple images at the same time.
Will that increase the total number of input layers?
No, it's just
32 by 3 when we started, for example.
Yeah, it will change to let's say n times 32 times 32 times n.
100 into 32 and 32.
Yeah, but it's not. You can think of it as a 4-dimensional tensor, but it's not really. Yeah, it's a 4-dimensional tensor now. Yeah, it's just batch operations. Yeah.
So in that case, how do you use training data means and variance for that type data? Like if there is
you have your training data, right? You keep a running count. Somehow, if you can get to know the activations, these are just functions of a layer, right? So ideally, you want the expected value of activations of all your training data. That's a single number. That's a single number per such per filter and per fiber. Per spatial region or whatever receptive field. Yeah. You have to keep running some, so it kind of increases the complexity. Yes. Because if you don't do this, then you are really, it's a different signal now, right? So all you're doing is just this. You add these two, and these are still differentiable functions, so you can do backprop. And it's empirically observed that it improves the gradient flows and it's less sensitive to initialization. So even if you have a slightly bad initial weights that you are starting gradient descent with, having a batch normalization helps. So this is a somewhat new technique. Came up after 2014, so probably it's not there in AlexNet, for example, or even in VGG. We saw in VGG there is no batch normalization. There was CONV, pool. There were like 15 or 19 layers there. Yeah. So that's one thread of how to deal with weight initialization, and it's a modeling thing. I've changed the structure of the network. Second thing we're going to do is something called dropout. I don't know how many of you have heard at least the word dropout. In the context of neural networks, not in the context of academic. things, but yeah. Okay, so dropout is this. So you've seen L1 and L2 regularization, right? I mean, we saw that in just a classification pipeline that we discussed in lecture 0. So dropout is also can be thought of as a regularization. So we'll get to why it can be thought of as a regularization. But first, let's kind of understand what do we mean by a dropout operation, right? See, the idea is, this is our, let's say, fully connected network with one hidden layer. So during training, every time we forward pass, it can be a batch, it can be a single image, a batch of images or a single image. We'll set the output of a few neurons to 0 with some probability. Let's say, so here there are 4 neurons, right? So every neuron flips a coin with some bias, with some probability. Let's say it's flipping a unbiased coin. So with probability half, it will set its output to be 0. So that's what I mean. So there is no, so I couldn't delete these edges, so these edges are irrelevant. So they are 3-dimensional input. This is anyway output is 0, so these are not acting, these are not influencing anything. So 3 arrows, these 3 are going into this neuron, these 3 are going into this neuron, and ultimately you're getting the scores, right, in this. So that's what dropout actually just means. You just set the outputs of the neurons to be 0 with some probability for every time you do a forward pass in your training. So why do you do a forward pass? Because you're doing gradient descent. You have to do the forward pass to get the gradient values and do an update, right?
But why keep the neurons?
You are randomly dropping the neurons, so this neuron may be useful in next iteration, but not useful in this iteration. Yeah. So what is it doing? That's the operation. So let's interpret it, right? So first of all, it is making us use a smaller capacity of the network, because if you are dropping the neurons, it's essentially saying in one pass, in that pass, I'm looking at a smaller neural network, right? Because some neurons are gone, some edges, some weights are gone, so it's a new smaller neural network. So the capacity of the network is smaller. But capacity is just a subjective term saying how many functions I can express using that network, let's say, loosely. Then I can't express too many functions, not as many functions as the original network, because the original network had a lot more nonlinearities, a lot more neurons, so it can express a lot more complicated functions. So in that way, you can think of it as a regularization. I'm just shrinking my network in that particular pass somehow, right? By dropping the neurons, not somehow. Second thing is, it's forcing all the neurons to be useful, because if I drop this neuron, and this neuron was critical to kind of output, let's say that the input is a spam or not. Let's say it's just input is just an indicator vector saying whether the email is email contains the word send me money or something like that, money or something. So let's say there's some input. If you drop this neuron and this neuron was critical to kind of signal a high score for that class, then hopefully hopefully if I drop the neuron in one of the dropouts, there should be some other neurons which cover for it. In the sense, there is some redundancy that we are kind of forcing the network to learn, right? There's redundancy that we are forcing on the neuron on the neural network. So those are some 2 interpretations of what dropout could induce, right? Intuitively. Empirically, it's been observed that if you do this dropout, it does improve the stability of the learning process and get you to good validation errors or test errors on your classification task for large deep networks. So that's the empirical validation in terms of the accuracy of the task that you're doing. But intuitively, what's happening is either a little bit of regularization or a redundancy capacity building, right? You can also think of it as actually ensembling, and that's a little bit it's a 2-step thinking process. So do you know what an ensemble is? Okay, for those of you who don't know what ensemble is, when I said I'm going to augment the data and for any test image, I'm going to crop the data at the top left, crop the data at the bottom left, and again do a lot of predictions, and then I'm going to do an averaging or weighted, let's say, majority vote of which category that image belongs to. You can think of this averaging procedure as something like an ensembling, right? It's as if you had multiple predictions and you're just tying them together. And in fact, those predictions need not be from the same classifier. It can be from very different classifiers. One can be a deep network, one can be a shallow network, one can be a rule-based system, right? And in fact, you need to think of all these when actually you're in deployment, or if you're working professional, you don't have to stick with one classifier, right? So ensembling is just using multiple models to make predictions. So when you kind of drop some of the neurons, you're essentially think of it as like subsampling a network, right? So you can think of this itself as a neural network. Of course, it only has 2 neurons in the in its hidden layer, but that is a neural network, right? And in the next round, maybe only this neuron is dropped. That's a neural network, right? So that's a classifier. This is a classifier. So you have lots and lots of classifiers, and you are trying to and all these classifiers share parameters, right? Like let's say in the first forward pass, I dropped these 2 neurons. They have, at this iteration maybe they got some weights. In the second forward pass, I only dropped this neuron, right? Then I'm using the same weight. So that's all I mean by saying all these different classifiers that I'm generating, that I'm looking at every forward pass. They all have shared weights. Okay. That's what I mean by an ensemble of neural networks that share parameters. Is that point of view clear? We haven't yet got into what does this ensembling point of view give us, but at least you can think of it as an ensemble of a bunch of neural networks, because every time I do a dropout, I have a different neural network, right? At least I have an ensemble. I'm not. I haven't yet told you how I'm doing averaging, and that I'll tell you in the next in this slide. So first of all, higher probability means stronger regularization. That you saw. If I drop my neurons a lot, that means that the capacity of the network is much smaller. So higher probability means a stronger regularization. But let's focus on ensembling. At test time, instead of so ideally, since if you think of it as an ensemble, I have generated so many neurons by dropping all these hidden neurons in every forward pass. So I have generated so many neural networks, right? So at test time, it makes sense that I forward pass my, let's say, input through the first neural network, forward pass my input through the second neural network, forward pass through all the neural network configurations that were generated because of dropout, get all the predictions, then take an average, just like I was doing it here, right? With dot augmentation. So instead of doing those many forward passes, you can actually do one thing, which is perform no dropout. Just send the input directly all the way to the output, but you scale all the activations by the probability of the dropout. Okay. So it's just a so for example, if you remember that one hidden layer neural network, it was so f is equal to again I'm writing it. So this was the one hidden layer neural network, right? So this was the number of rows kind of determine the number of neurons here in the hidden layer. So actually I have that example. So if you drop out with the probability p, let's say it's 1/2 or something, 0.5, then originally, so this was the network, right? W2 with one hidden layer we have already seen, and lecture 1, lecture 0, and so on. Then with dropout, all I'm trying to say is at test time, you just have to bring in that parameter p, the probability of dropout, which you dropped every neuron, as a part of your forward pass. That's all. And miraculously, it works out that with this, you are essentially doing ensembling. As in, it's as if you are doing many forward passes and taking an average. Okay. Yeah.
Is the probability p specific to one neuron?
No, it's specific to every layer. I mean, you can make it specific to every neuron if you want to, but then you'll have to keep track of that somewhere else. If you make it part of the layer, then it's just a multiplier like this as a scalar.
But we're dropping neurons at a time, right? Or are we
Yeah, I mean, it's a single parameter can determine dropping of all the neurons, right? let's say I say dropout with probability half, then every neuron I'll flip a coin with probability half. It's the same parameter. I don't have to associate one coin flipping, one dropping, probability parameter for every neuron. I can say all these neurons have the same probability of getting dropped out, right?
How do we come up with this probability number?
This is a parameter that you need to decide. It's a design choice again. Just like for the con layer, the number of filters, for the pool layer, the stride and all that. So P is a parameter. It's like a hyperparameter. You can try to optimize, but I don't think people do. So that's it. So that's dropout, and it's empirically observed that it does stabilize your learning process and give you decent results. The reason why I'm discussing about data augmentation or model tricks like dropout or batch normalization or weight initialization is because for really small networks like a 2-layer network, it really doesn't matter. So you'll probably not see much, many things in your assignments and stuff. But if you really train, let's say, 4-layer network, unless you take care of these things, and you can incorporate these tricks or take care of weight initialization properly, if you don't do that, you will not be able to train your network. And that's a lot of effort, kind of hidden effort from the results that you see from AlexNet and ResNet and so on, right? Okay, so we have revisited a little bit of a couple of concepts in models and one concept in data. Then we're going to look at now engineering deeper networks. So how did these guys get the AlexNet going? How did these guys do an image classification as well or better than humans, right? So we'll see what are some of the things that they do. So remember that we generally have millions of parameters in deep networks. So the question is, like, let's say you're designing a CNN or you're working on deep learning, and you want to investigate, like, if you want deeper networks, how do you handle the computation? How do you handle memory? And these types of things have been documented and have been published. So we will look at some of these issues when you try to scale up your CNNs, right? So one thing that you will kind of easily recognize is vectorization, but I'll talk about a couple of other things that you might not have seen. Okay, vectorization concept is very simple. Yeah, any question? So vectorization is very simple. We have already seen this in the example class, right? So if you have a, let's say, input vector, this max operation is an element-wise operation, and you get an output vector. You can do this element-wise operation by a single call, roughly, right? In NumPy, if you do a max operation with 2 elements, you can actually pass on vectors, and you can compare the time speed up with respect to doing a for loop and doing a max operation, right? So your low-level libraries kind of take care of doing vector operations. Okay. So let's look at something more interesting. So remember the CONV layer, it has to do filter computations, right? What do I mean by that? So a filter has to do an element-wise element multiplication of its block with a spatial field, with a block in the input tensor, right? That's roughly what it's doing, element-wise multiplying every entry and then outputting a single number, and that it's putting it on the 2D activation map, right? So let's say the feature map is height times width times some depth C, and you have D filters, and each is height times width, which is the same dimension, and another depth. Depth is same as the input depth, right? I'm just representing filters as blobs because those are the parameter tensors, right? 3D arrays. What you can do is the following, and this is an interesting vectorization. You can actually reshape K cross C receptive field column with K square C elements, which just means vectorize this block. Okay, so you have like this neuron is supposed to look at the top left spatial field and also the depth, right? So you kind of linearize that field and you'll get a vector which is of this dimension, K square C dimension, and you can do that with all the areas which are being all the areas which will be seen by all of these filters. Okay, all of these filters will look at all these areas, so it's the same thing, right? one thing, can you notice one thing here? There is redundancy. Can you say why there is redundancy?
You're going to do common elements.
If you take two of these columns, a lot of the elements will be the same. Because if you take one stride, it's basically most of the elements are the same. It's just you deleted one side here and you have added one dimension there, right? So there will be a lot of redundancy, but apparently that redundancy is outweighed by matrix operations, and that's why we are converting it into a matrix, a 2D object. You can also linearize your weights, right? K cross C is just K square C rows, right? And I've just stacked them in a horizontal manner. So it's D is the number of rows here, right? And then you can see the structure is obvious here. You can just multiply those two and get a result, right? So you have actually applied all the filters or all the input data, all the input tensor at the same time in one matrix multiplication. And of course, now you also need to reshape your output to make it into tensor. I mean, as needed by the next layer. So this matrix multiplication is quite fast, and that's what is the kind of the secret sauce for GPUs. They can do really good matrix multiplications. So you can actually even make it faster by trying to kind of squeeze in more and more of matrix multiplication. So do you guys know what is the time complexity of a naive matrix multiplication? Matrix multiplication. Huh? You have two options, n square, n cube, let's say.
N square. N cube.
No, it's n cube, right? You want to multiply two matrices, right? For every output element of your matrix, so C is equal to, let's say, A times B, then Cij is sum over, it's a double sum?
Single sum.
Oh, it's a single sum. Oh, what was the dimension here? It's a D cross E. It's basically picking a row and a column. Right. So this is n operations, and there are n square such operations, right? It's not clear. N operations here, right? And you have n square entries in C. Each entry is having n operations, so n cube. But anyway, what I'm trying to say is that GPUs are kind of trying to take advantage of matrix multiplications, but you can also focus on trying to make those matrix multiplications faster. But you can only do that for very specialized architectures, because if you are looking at general purpose matrix multiplication, it's been already optimized heavily by a lot of people. You can also use fast Fourier transforms, because if we use the name convolution, although we kind of looked at it as just matrix multiplication, it's actually also, you can think of it as a convolution in the signal processing sense, and so you can actually use fast Fourier transforms. And fast Fourier transform, by the name fast, it just means that you can do the convolution in a very efficient way. Okay. Okay, so let's look at vectorization was just a starting point of how to get these deeper networks, right? Once you deal with millions of parameters, you really want to take care of how many multiplications are happening, how many layers, and all that, right? So let's look at just an example of a couple of new architectures. We have seen a regular CNN, and we were kind of alluding to AlexNet all the time, and we also saw the VGG's layer diagram, and it's just a bunch of convs and then max pools, convs, max pools. That's okay, that's all clear. But the newer networks, for example, 2014 winner. So if you remember, VGG was second place CNN in the 2014 challenge, and VGG had 180 million parameters. These guys, this is VGG had about 15 to 20, actually 19 layers. These guys have 22 layer neural network, but it's no more. It's not conventional neural network anymore. In terms of block diagrams, they actually have a pooling operation, 1 cross 1 convolution, which is an extreme limit of k cross k convolution that we are seeing. 1 cross 1 just means looking at a receptive field of size 1 and the input tensor. They have many other convolutions stacked up. So on this they call it a module, and so this is one block of their layer of their CNN. So the whole internal structure has changed. For us, the internal structure was a sequence of let's say 3 cross 3 filters, and we were getting tensors to tensors, right? Here also we'll get tensors to tensors, but it's just that there are a lot of intermediate convolution operations going on, and there are also pool operation going on. And this network only had 5 million parameters. So that's a very, very huge reduction in the number of parameters. Okay. What is the max pool? The max pool you have seen, right? The pool. Max pool just means pool layer. So the way you do the pooling operation downsampling, if you're taking the maximum of the local entries, then it's called max pool. If you're taking the average, then maybe it's called an average pool layer. Softmax. Softmax is your transformation, right? Softmax transformations of scores you've seen. Softmax is just corresponding to the logistic loss, and then the step before that, if you get scores, you change them into probabilities, right? That's the softmax operation. E to the power score divided by sum of the e to the power scores. Yeah. So ResNet, which is the next year's winner, it did something. It didn't probably do as complicated as the Google Net, but it had a notion of a residual block. So for it, this was a layer. This is a block for it. It has too many layers, so let's not count in terms of layers. Okay. By the way, this is an order of magnitude more than what we have been looking at. 150 is too much, right? I mean, can you imagine gradients passing all the way back to the weights at the beginning? But anyway, so the kind of key trick is they have a convolution batch norm, ReLU convolution batch norm, and then they have an addition of the input tensor after these many operations, and then again a ReLU and then an output. So this is a block for them, and they have many such blocks such that the height of the network has 150 layers. Okay. Actually, I'm just flashing these a couple of architectures. If you look at their papers, they will try to reason why such an architecture may make sense, but I don't think it's mainstream yet. So, in terms of practice, at most what you may be doing is to actually take that pre-trained network and do your fine-tuning at the later layers, and you have the choice of designing the later on layers, right? I mean, if you remove the fully connected layer at the end of this of a VGG network or a ResNet network or this network, then you may add a fully connected network, you may add a couple of other convolutions, or you may do a fine-tuning at the end. So you'll probably just use them as feature extractors or just fine-tune. So you can look at the references to kind of intuit why adding this additional input makes sense. Okay. So that's just a snapshot of a couple of recent architectures. So they haven't departed too much from what we've already studied, except for a couple of tweaks, and apparently that tweaks kind of make them classify better than humans. So you may want to check them out. But with 100 layers or whatever, 20 layers, it's still kind of hard to train those networks on a CPU machine for sure. I mean, you cannot train these on CPU machines. It will take months. So even a machine with let's say 1 to 4 GPUs, it will take 3 days to a couple of weeks to train let's say the VGG network or the Google Net. So what the Microsoft or Google, who kind of submit these networks for doing really good classification, they build really good software systems. Like for example, systems such as TensorFlow, which Google has open source. It takes care of something called data and model parallelism, and we'll just try to kind of get a exposure to what does it mean by model parallelism and what does it mean by data parallelism. It's a very simple concept. Data parallelism is as follows. You kind of break your data. I had 1.4 million images, or let's say 14 million images. I break my data into several blocks, and I put these blocks in different devices, different computers. Okay, and I'm gonna work on my gradient updates. So there will be a bunch of computers which will just store the parameters of my network, let's say the VGG network or AlexNet or something like that. And then I'm gonna read the parameters and do the forward-backward pass and just send back the gradients to the parameter machines. Okay, it's just a distributed architecture where data is split across multiple machines, roughly in a cluster. You also have something called model parallelism, where weights are kind of split across machines. Each machine may have the local copy of the data, but it doesn't have the full copy of the network itself. Because if you saw, let's say VGG has 180 million numbers. So if you have don't even have RAM to kind of store those many numbers in your GPUs, let's say, you will have to go across GPUs or across machines. So that's what model parallelism means. Data is already there, but you have to split your model, and then therefore there will be interaction. You'll have to pass the gradients across each other because they'll all influence each other when you do the gradient update. Okay. One final trick or practice is trying to play with the precision as well. So these high performance CNNs also kind of try to see if they can use smaller precision actually. And it's been observed that smaller precision does not impact performance much. You can actually play with this by trying to change the NumPy data type. So if you kind of, let's say you initialize a NumPy array and you look at type of the NumPy array, right? You'll see the data type also being printed. Typically, I think it defaults to float 32. You can try to change the data type and see how long your computations take. For example, if you're linear classifier or a two-layer network, you can change the data type and see how long this, in terms of, let's say you're running 1,000 iterations of gradient descent, backward propagation, and how many seconds it's taking, right? So for example, the fastest, I think here they're showing how long does it take to do a single forward pass for AlexNet. If you kind of change the precision, so you can see that if you have floating point 16 precision floating point, one forward pass takes 25 milliseconds. Okay, I think and here 128 is a batch size, and you remember from AlexNet that the AlexNet input image was 224 cross 224 cross 3. Okay, so actually there's a paper from 2016. It says you can also use 1-bit activation. So activations and weights. So where every weight is just 1 or 0. So you just need 1 bit to represent it. Where it's just that they use higher precision for gradients, and they're saying that with this we still achieve almost the state of the art. They are not beating the state of the art. Okay, so those are the things that people concern themselves when they build these really large scale CNNs. And fortunately for us, we are going to just use pre-trained networks, ideally, unless somebody is ambitious to train. Okay, so in summary, what we saw is we tried to look at visualizations to understand how CNNs work. That was in the last class. We tried to kind of change the objectives and see a couple of threads. That was the neural style transfer and deep tree. And then we saw how you can get started on using a deep learning stack for your application when you have small data set. We also looked at neural nets in practice, especially this practice of data augmentation that people do for vision, and also the impact of initialization, batch norm, and dropout. These are a couple of new techniques which you can use for training deeper networks. And then we just touched topics such as vectorization, architecture changes in the newer generation networks, use of parallelism, and use of precision to kind of train faster. Okay. So jump starting is an excellent way to get a deep learning solution working. So there's no need to search for large data sets for your task. If you're going to work on text in your projects, next class we're going to look at word embeddings and RNN. So you should be comfortable, you'll get comfortable with that by next class. So this class, by this class we are just ending our journey with vision datasets. Okay. We haven't seen VGG in Keras, but I have put up the link on the slides. It's the weights file is about 500 MB. Okay. But it does capture, not 160 million. I think it's a slightly smaller network, 16-layer network. So maybe 120 million numbers. So we can actually run that and see how it classifies. To train the state-of-the-art networks, you want to rethink data models and optimization. So we have not touched optimization yet. We can, and it's not needed for even state-of-the-art networks. Even for smaller networks, there are some tricks on top of the regular gradient descent that you do. You're changing the learning rate, but you can also change other things. And if the deep learning system is core to the business, then you want to look at those engineering best practices. Okay, that's it for today.